Hello and welcome back to our machine learning course. I'm Joaquin van Schoven and today we'll talk about handling imbalanced data. Now, data imbalance can occur in different ways in your data set. It could, for instance, be that you have a lot of positive examples and a few negative examples. That's lots of positives and maybe only a few negative points thrown in, right? Now, if you would normally train a model on this, these few points will have a relatively small effect on the loss function, and your model may be tempted to just ignore these points. Right? If these points are important, you don't want that, so you want to correct this imbalance somehow. Examples of this are, for instance, credit card transactions where most transactions are good, but a few of them are fraudulent, or it could be medical data, for instance, x-rays, where most x-rays are normal and a few of them have, for instance, a cancer or something else you want to detect. And yeah, so that you want, again, of course, you do want to make sure that these minority cases are taken into account. Now, so another way this can happen is that your data set is fairly balanced, so there are more or less the same points for different classes, but still the negative class in this case, for instance, is more important to get right, and we still want to increase the weight of these negative points so the model pays more attention to them. And we've already seen two ways of solving this. The first one is class weighting. Right? So here we change the loss function so that the, the minority class has a larger weight. So if you have a point, so typically most loss functions are a sum over some other loss, like the difference between the predicted and the actual target. Just a simple one. And we could add a weight about each class so that, class weight, so that if this error here corresponds to the majority class, it has a smaller weight on the loss function, and if this point I is about the minority class, we can give a higher weight to this loss, right? And that way we can force our learner to pay more attention to the negative classes or to the minority classes. In practice, you can do that by adding class weight. So normally you would have to give a value for each class. If you use balanced, it would set the class weights in such a way that each class is equally represented in the loss function. So if, for instance, you have 5 times more positive than negatives, it would set the weight of the negative class 5 times higher than the positive class. Another thing we can do, we can change the prediction threshold to minimize false negatives. Right? So say you have a prediction and probability of that is 0.4, right? But this is actually a positive point, and a model predicts 0.4, so that's a false negative. If we put a normal threshold of 0.5, this will indeed be predicted negative, but we could reduce this threshold to 0.3, and then this point is with positive, right? So we don't have a false negative anymore. And yeah, so we can change this threshold, as we've seen before, to trade off false negatives for false positives. Now, these techniques are fairly used, and definitely these are perfectly good techniques when you have imbalanced data. Now, in this video, we'll focus on a few things we can do in the pre-processing phase to balance the data beforehand. The first thing we can do is we can resample the data to correct the imbalance. For instance, we can undersample the majority class, or we can oversample the minority class. Or we can use some model-based techniques that tell us which samples to remove or which samples to add. We can indeed add synthetic samples, so we create new training points in our data set for the minority class. And finally, we can build ensembles in which each individual model, for instance, each individual tree, is balanced. Okay? And then we can also use combinations of all these. The first and simplest technique is called random undersampling. You can see this here in this figure. So if this is our original data set, so we have a lot of blue points, a few orange points. What we do is we copy over all of the orange points here, and for the majority class, blue points, we randomly sample some of them, and we add them to our new data set. Right? It's a very simple technique. It's very cheap. Of course, you do throw away quite a bit of your data, and that's not ideal. If this is too harsh, what you can do, instead of going for a 1-1 balance, so blue and orange are equally represented, you could allow, for instance, a 3-to-1 balance, so you have 3 times more blue points than orange points. So it gives you some way to control this amount of imbalance. If you have a multi-class problem, you just do this for every class. So you copy the minority class and you undersample each other class so that in the end all classes are balanced. And this technique, although it's, well, in this case it doesn't do so well, right? So original data set had an AUC of 0.83, and after undersampling, this went down quite a bit. So it's not ideal here. But if you have a large data set, you probably have a lot of points you don't really need. And in that case, first of all, you may get even better performance, or you may end up with a much faster model because you needed less points to train, so your models will be faster to train and may have similar performance. Instead of randomly undersampling, you can also use model-based undersampling. So here we use a model to tell us which points to remove. And the simplest way of doing this, or the most common way, is to use KNN. This is called edited nearest neighbors. So what this does is it takes a blue point, it looks at the neighbors. If this point is misclassified by KNN, then it is possibly a noisy point. It's a blue point in an orange region, right? And then we remove that point from the data set, or from the balanced sample. Instead of using KNN, you can also say that all neighbors should be of the correct class, otherwise it's removed. Okay. Yeah, what this does basically is it sort of cleans up the space. So here we have this very noisy region, and here you can see we have removed points in this region so that now this is more clean, and your model is probably more likely to learn a model which makes correct predictions for this region. And all the rest of the points are not affected at all. Now the opposite idea is called condensed nearest neighbors. So here you move all the majority samples which are not misclassified. So what that does, it gives you all the orange points, and it keeps only the hard points which are hard to predict. Right? The idea being that if you force the model to look at this space and remove the confusion basically by the rest of the space, you may end up with a better model. Now, in practice, I haven't seen this work so well. Right? So you can try it, but it's not the first thing I would try. Another thing you can do is random oversampling. So here we copy all the blue points over, and then we sample the orange points here with replacements until balanced. Right? So sampling with replacements means that we can pick the same point multiple times. So, and this is what will happen, right? So you will resample these orange points over and over again, so you'll end up with a lot of duplicates. But the upshot is that if you look at the numbers, the datasets will be balanced. Again, if you don't want to have a 1-1 imbalance, if you can get away with a 1/5 or 1/3 imbalance, then that's fine. And you don't have to oversample that much. One downside of this is that this makes the model more expensive to train, right? Because you have many more data points, possibly many more data points, while it may not always actually improve performance. So here it actually goes down a tiny little bit. And also, this is very similar to giving the minority class a higher weight with class weighting. So, well, because if you would sample every point 5 times, it would be exactly the same as giving the minority class a weight that's 5 times higher. Because every point will be 5 times in your train set, which means it will occur 5 times in your loss functions, which is equivalent to just having it there once and increasing its weight by 5. Okay, so it's totally equivalent, except that it's a bit more random than just using the class weights, and it's more expensive as well. Another technique that's very popular is called SMOTE, which stands for Synthetic Minority Oversampling Technique. So what you do is you pick a minority point. So I pick an orange point here, and then I pick a neighboring minority point, which is here. And then I create a new point, which is somewhere in the middle between them. It doesn't have to be exactly in the middle. We typically look at a normal distribution in the space, and we choose a point somewhere in the middle nearby. Okay, so it's uniformly. This is a great technique to create more data points. So here you can see, for instance, this is original data set, and here we have created new points in between all these orange points here. The obvious downside of this is that you are creating artificial data, and this data may be wrong, right? It may not reflect real world. So, yeah, in that sense, it may be dangerous to do this. Of course, you could always try this and see if the model actually performs better on your test set. Which brings to the next point, which is to never ever uh, use SMOTE on the test set, because if you create artificial test sets, then yeah, your model is basically worthless. Well, the evaluation will be worthless. There's one variation of SMOTE, which is called ADASYN, or adaptive synthetic, which is very similar, but instead of starting from a random point here to generate a new point, you start with a hard point. Hard point similar to the KNN before. If there's a point which is misclassified by a KNN, then it's a hard point, and that's the point we start from to run SMOTE. And then we take another point, neighboring, and then we generate points in the middle. It's a small variation that sometimes works a bit better. Then you can also combine techniques. So for instance, one very popular way is to run SMOTE, right? But then also clean up the space here with edited nearest neighbors. Right? So if you compare this to normal SMOTE, we can see that we have many orange points, but you also have some blue points in between, right? And these blue points may still throw our algorithm. So what we could do is combine this with edit nearest neighbors to remove the blue points which are still in there. So we end up with a nice clean orange space here. And looking at the performance, this actually seems to work well. The final method is called ensembling resampling. So what you do here is, so this is actually not a preprocessor. It's not a step in the preprocessing pipeline, it's a learning algorithm. It's basically a small variation of normal bagging. And there are different versions of this. The most straightforward version is balance bagging. So here you use normal bagging. So you take a bootstrap of your data, You sample with displacement, right? You take a sample of your dataset, and then you undersample that bootstrap so that the data is balanced. And only then do you train your first tree on it. And then you take a new bootstrap, you undersample that, you train your model. You take a bootstrap, undersample, train your model. And you do it n times, and you end up with an ensemble. The benefit of this is that you don't throw away so much data. And so in this figure, this is basically the sum of all the 10 random bootstraps which are undersampled. So each of these 10 is undersampled like this. But then we repeat this 10 times and add those 10 times together, we can see that we actually cover most of the original data points, which is good. We don't throw away information. There's an easier version of this, which is called Easy Ensemble. And what that does, it basically forgets about the bootstrap. It directly samples an undersampled balanced training set, builds the first model, then builds another random undersampled dataset, trains the model, and so on. You can use this with any model you want. Traditionally, this is done with AdaBoost, but you can, of course, use any base learn that you want. Okay, which one of these will actually work the best? So let's compare. So to evaluate that, you want to evaluate it on a certain learner. So say, for instance, that we want to use a supervised machine at the end. Right? Then we can look at how different methods perform. So first of all, we can try undersampling. That actually already works quite well, right? So we had our original data set, 83% AUC. After undersampling, we get 96 AUC. That's very good. We could try add nearest neighbors. That's even better. Condense is probably worse. Yep. Random oversampler. It's also very good. It's not as good as add nearest neighbors, but it's quite good. SMOTE gives us also quite good results, 96%. AdaSyn will be more or less the same. Yeah. And then the easy ensemble, yeah, also more or less the same. Balanced, slightly worse. And then we have SMOTE width at the nearest neighbor, and this gives us very good results. We get 0.999 AUC. Right. So it's quite hard to predict which method is going to work well because, yeah, it really depends on how clearly separated the negative points are, the amount of the imbalance, the amount of data points. All of these play a role, and it's quite hard to predict which is the optimal imputation technique, imbalance correction technique. We could also try to see what happens if our model is a random forest. So likely this will still work quite well. It's a bit slower. So if we try normal undersampling, yeah, it's better than normal, but yeah. If we try maybe random oversampling, that's a lot better. If we try SMOTE, it's actually a bit worse. If we try SMOTE and editing, that's quite good, 998. And if you go meta and we use a balanced bagging classifier, it's quite expensive. We get AC 0.999. So I say meta because this is a bagging classifier in which the base model is also a random forest. Right? So yeah, this is quite expensive, but also yields you quite good results. How do you apply this in practice? Well, in scikit-learn, it is not so well supported. There's a much better package for this called Imbalance-learn or Imbalance-learn. What this does, it follows a fit sample paradigm, which is similar to fit transform, except that it also affects the Y output. So remember, in the normal fit transform, it basically only affects X. We do give it Y because it needs it to compute or to fit the transformer, but it doesn't affect the Y. But in this case, we do have to affect the Y because we're creating new samples, right? Yeah, so we have to use it's called a fit sample paradigm. Imbalance-learn has a lot of different techniques you can use. For undersampling, it has a random undersampler, addless nearest neighbor, condensed nearest neighbor, and so on. It has SMOTE, it has normal random oversampler, it has ADASYN, it has also all these combinations. And so for all of these, we just create one. So here we create SMOTE. And then we run fit sample on our data X, and this gives us our resampled, balanced data X and Y. Right? You can also use Imbalance-learn pipelines. Now, Imbalance-learn pipelines are not the same as a scikit-learn pipeline, but they are compatible with things like rich search CV and so on. So you create them in the normal way, like make pipeline, only that this make pipeline is a function from the Imbalance-learn package and not from the scikit-learn package. Right? So we create a pipeline with a balancing technique and our final model. This creates our balanced pipeline, and then we can give this to cross-validate to get the scores. We can give this to a grid search. So for instance, if you want to apply SMOTE, but you also want to optimize the number of k neighbors, you can do that in a grid search. Right? This will optimize SMOTE so that it uses the optimal number of neighbors. This is true for all the methods except for the ensemble techniques because they are not preprocessors, they are normal classifiers. They have the normal fit predict interface. You just create, for instance, an easy ensemble classifier. You use your base estimator. In this case, we use a vector machine, and then we fit it on the training data. Finally, how does this work on real-world data? And so here we show the ROC curves for different data sets. So this case, first we look at the speech data set. And here we see this is a quite hard data set. If you don't do anything, then the original performance is very close to just, well, this is one, the diagonal line. Right? So it's diagonal line somewhere here. So it's very close to the diagonal. So this is not a good original model. We can see that basically any imputation technique gives you a better result, a better ROC curve. Except perhaps for edited. Well, it's edited is a bit worse in the beginning, but then gets a lot better afterwards. So if you are in the low false positive rate, so if false positives are very important to you, you want to use, for instance, in this case, the random undersampler does well here. We have the balanced bagging one, but also SMOTE is here, and so on. Yeah, so you could choose a balanced correction technique depending on where you are. Overall, it looks that balanced bagging and these ensembles are both doing very well. Also very well is SMOTE here, and the light blue one ADASYN is very similar, and then undersampling also does quite well here. Okay, we could also look at other data sets, for instance, and your mileage will vary a lot here. So say we look at the mammography data set. Yeah, so here they're all very, very close together. There are a few worse, like the oversampler, and I think SMOTE does not so well here. but the other ones are very close to each other. If you use the MC1 dataset, it's quite a small dataset, so it's a bit stepwise. Here we also see that the ensembles do best overall, and undersampling again does also a pretty good job. And most of them are still better than not doing anything. Okay, that's it. That's the last part of our course on data preprocessing, and it's time to wrap up. So first of all, data preprocessing is probably one of the most crucial steps in machine learning. You can typically get much better performance if you spend some time preprocessing rather than fine-tuning your machine learning models. First of all, scaling is very important for any method that has some kind of distance, like KNN, SVM, neural nets. If you don't scale the data, they won't work well at all. Some algorithms also can only handle numeric data, and for those, it's very important to encode your categorical values. It also depends on implementation. So, for instance, scikit-learn, no current technique can actually handle categorical features. There are some trees that can do that, but they're very new. Otherwise, you always have to categorically encode the data. Selecting features is, again, one of the best things you can do. So either selecting features helps you reduce overfitting, or it can make your model be smaller and faster without losing much accuracy. It depends, of course, on how many features you have. If you have a very high dimensional data set, selecting features is likely more useful than if you have a very low dimensional data set. Feature engineering is creating new features based on existing ones, and this is very useful to make linear models more flexible. If you have missing data, it's often better to impute the missing data rather than just remove it. And if you have imbalanced data sets, it definitely pays to correct this imbalance before submodeling, or to use a modeling technique like this easy ensembles, which handle the imbalance natively. Now, all of these techniques should be put into pipeline, because this will ensure that there will not be any data leakage. Because if we have to, most of these techniques should not look at the test set in any way, because they may leak information, and pipelines are probably the best way to avoid that. And finally, we also need to not only choose right preprocessing techniques, we also have to choose right model, and the right preprocessing techniques may very well depend on your model. Right? So you could use cross-validation to find the optimal combination, but this is a pretty large search space. Right? So you could spend a lot of time doing cross-validation until you find a good model. Now, luckily, there exist smart techniques that do this for you. This is called automated machine learning, which is something we will cover in one of the next lectures. So that concludes lectures on data preprocessing. I hope you enjoyed it, and see you next time.